Today I will be reviewing organic nomenclature for organic compounds with multiple functional groups. There will be a quick review of the different functional groups, including the order of their priorities, and polar properties of some of these functional groups, as well as an assortment of sample problems at the end for you to pause and try. Alright, so we have alkanes, alkenes, and alkynes, as well as halides. Alkanes are not actually a functional group, they lack a functional group, but they are important for organic chemistry, so I chose to include them here. To continue with alcohols, we have ethers, there's aldehydes, ketones, carboxylic acids, and then lastly we have esters. And the main difference here between aldehydes and ketones is that the aldehydes have a double bonded oxygen on the end of the chain, whereas the ketones have a double bonded oxygen in the middle of the chain. Each of these groups have a suffix, so alcohol it's all, ethers it's oxy, it's a bit special, but I will show you an example later on to further clarify this. Then there's aldehydes with al, ketones with -one, carboxylic acids with oic acids, and esters with O8. Here are some more examples of some functional groups. So we have the amino functional group. Firstly, the primary amine, the secondary amine, and then finally the tertiary amine. So these all have a suffix of amine, and the main difference between these three different types of amino groups is the placement of the nitrogen in the carbon chain as well as the different chains that are attached, or the number of chains that are attached to the nitrogen. So we also have aromatic hydrocarbons. So this first one is a benzyl, and the second one is a phenyl. In a benzyl, the benzene ring is separated from the rest of the chain by, for example, a methane group, whereas the phenyl has the rest of the chain, or the carbon chain, directly attached to the benzene ring. So now we will get into the rules for when you are naming a hydrocarbon that has multiple functional groups present. These are some things you want to consider while you're naming them. So firstly, you want to find the longest hydrocarbon chain. So here I put a little example. You want to find the longest continuous hydrocarbon chain. Second, you want to identify the highest priority functional group, which we'll get into in the next slide. Then you want to number the hydrocarbon chain to give this functional group that has the highest priority the lowest number. And then finally, you want to identify any other substituents that are present in this hydrocarbon, as well as their position on the chain. An important part of naming a hydrocarbon is identifying the highest priority group. So first we have carboxylic acids with the highest priority. We have esters, amides, aldehydes, ketones, alcohols, amines, alkynes, alkenes, alkanes, ethers, and finally alkylyl halides. It is important to note that alkanes, ethers, and alkylyl halides all have the same priority, so when you're naming them, if they're all present in a hydrocarbon, you would go off of alphabetical order. I didn't previously mention amides, but it's when a carbon is double bonded to an oxygen as well as bonded to a nitrogen and then the rest of the chain. Now that we have covered some review, we will be going into the polarity of functional groups. So what I found is the greater the polarity, the higher the priority of the group is. And this is just the functional group, not the entire molecule. As a quick review, a molecule is polar if there is unequal sharing of electrons amongst the bonding atoms. So to expand on what I mean by this is here we have alkanes, alkenes, alkynes, and aromatic. Alkanes are still not a functional group, but I included them here as well to show the differences between the polar properties of alkanes, alkenes, and alkynes. So to begin, in alkanes there is no hydrogen bonding present. There are also no electronegative atoms, so this is a nonpolar molecule. Next, we have alkenes, which have the double bond there, and these are very similar to alkanes. However, they are a bit more polar because they have this double bond, which means that their orbitals are bigger, in particular their p orbital, which thereby increases their polarity. Next, we have alkynes, which are also similar to alkanes and alkenes. However, they still are a little bit more polar than these previous molecules. And this is because they have a larger orbital, again the p orbital, because of the increase in the pi bonds present. Next we have the aromatic groups, which are more polar than the above functional groups, and this is because they have even more double bonds present in their structure. So because they have more double bonds present, they have more pi bonds and that increases their p orbital in size, which also increases their polarity. They also have the ability to make more extensive hydrogen bonds, which also increases their polarity. To continue on, I grouped these different functional groups based on similarities between their polar properties. So as you can see at the very top, we have ethers and halides. So these two functional groups have a polar atom added to them. So for example, oxygen could be added to either of them. So this increases the electronegativity, which also increases the polarity of the functional group. Next, we have aldehydes, ketones, and esters, and I have the structure there so you can see them. So these have a larger dipole moment because of the added carbonyl group, which is composed of a carbon atom double bonded to an oxygen. And since oxygen is an electronegative molecule, it increases the polarity of the functional group. In addition, the double bond also increases the polarity because of the increase in orbital size. Next, we have amines and alcohols, and these two functional groups have hydrogen bonding present, which increases the polarity. And it also does have a higher boiling point. So alcohol is slightly more polar compared to amines because oxygen is a more electronegative atom than nitrogen. So next we have carboxylic acids, which are the most polar. They have extensive hydrogen bonding, which we know increases the polarity, and rather than having only one oxygen, it has two, and one of them is double bonded. So this double bond increases the orbital size, which increases the polarity, and carboxylic acids also have a greater dipole moment than the other functional groups. We'll finish off with a few examples, and I encourage you to pause and try and do them yourself. So with this first question, I want you to pause it again and try and find all of the functional groups present in this molecule. So hopefully you've paused the video, now we'll go through it together. So here we have an ether, and we can tell because the oxygen separates one chain from the other. Next up here we can see that there's an alcohol, but we see here that this aromatic group is actually a phenol because the alcohol is directly attached to it. So that'll be labeled as phenol. Then we can identify the amide because of the nitrogen attached to the carbon, which is also connected to an oxygen by a double bond. And then finally, we see an alkene here. This molecule that we just identified is actually capsaicin, and it's used as a topical treatment for arthritis pain. Here are some more examples. Please pause and try these by yourself. Now we will go through the answers together, starting with the top molecule. So we will first identify all of the functional groups present here to determine the priority. So here we have an alcohol, which I'm going to label hydroxy, and then we have a ketone below. We know ketones take priority over alcohols, which is why I named it hydroxy. So next we're going to number the carbon chain to give the ketone the lowest number, and then we're going to identify any other substituents that are present. So we have a methyl group here. So next, keep in mind alphabetical order and the numbering. So it's going to be a 5-hydroxy because the hydroxy group is located on the 5th carbon. Then we have a 6-methyl because, again, the methyl group is located on the 6th carbon. And then we have a pentan, 2-one. It's a pentan because it's a 7-carbon chain, and then the ketone is identified by the 2 and the one at the very end of the molecule's name. Notice that hydroxy goes before methyl because of alphabetical order. So for the next molecule, again, we're going to label all of the functional groups and identify those. So here we have carboxylic acid, we have a hydroxy, then we have a chloro, and then we have an ether. When there are many functional groups present in the molecule, I usually like to label them beside just so I don't miss anything. So here we have a 5-carbon chain, so it's going to be a pent. We have a carboxylic acid at carbon 1, we have a hydroxy group at carbon 3, we have a chloro group at carbon 4, and then we have an ether, which is the special case I mentioned. So because on the smallest chain attached to the oxygen, it's a methyl group, it will be methoxy, and then the rest of the name will follow. So finally, to name this, carboxylic acid is our highest priority group, so the name will be 4-chloro, keeping in mind alphabetical order, 3-hydroxy because the hydroxy group's on the 3rd carbon, then it will be 5-methoxy there because of the ether, and it will finish with pent because it's a 5-carbon chain. It will be pentan followed by oic acid to account for the carboxylic acid. Thank you for listening to my presentation. I hope it was insightful and that I was able to increase your knowledge on the polar properties of functional groups and one reason why the functional groups are in that specific order of priority.